All right, let's take a look at practice problem number 1 associated with sample problem E. Here, we will see one of the things I dislike the most in the world of science, and that is lame problem introductions. Measurements made in 1910 indicate that the common flea is an impressive jumper given its size. Just so you guys know, none of that's important to this question. I know you thought it might have been. It's not. Assume that a flea's initial speed is 2.2 meters per second and that it leaps at an angle of 21 degrees with respect to the horizontal. So let's establish our coordinate system here, right? We have plus, plus, minus, minus, and we have a little jumper. And let's just assume that the flea is kind of jumping this direction. And so what we'll have here is, we'll call that flea. It's jumping and it has a velocity, okay, which is going to be the resultant of a triangle of two vectors here, is 2.2 meters per second. Okay, we know that information. And it is jumping with at an angle of 21 degrees with respect to the horizontal. So here's my horizontal. So with respect, meaning from horizontal, that's 21 degrees. Maybe you guys can see that. I probably drew it too small. So we have here an x component of that velocity and a y component of that velocity. Okay, so let's do it here. If the jump lasts 0.16 seconds, what is the magnitude of the flea's displacement? Okay, so we're actually going for a displacement. So our answer, because our velocity is using meters per second, and we're going to use time to cancel out those seconds, our displacement will probably be reported in meters, is what it looks like. And then we have a second follow-up question that says, how high does the flea jump? Okay, so we have horizontal, or x component, and have how high, which is going to be our y component. So we're actually needing to come up with two answers here. Now, in general, we actually are going to be using our kinematic equation that looks something like this. Hopefully it looks exactly like this. That means I would be doing something wrong. Okay, so we have this kinematic equation to find total displacement. Now we need to do a displacement in the x direction, and then we're actually going to be looking for a displacement in the y direction. But there's going to be a little trick that's going to use a definition when we get to the delta y. But you'll notice that the flea has already jumped. Okay, the flea has already applied this force. It's leapt, and so it's going to have a constant speed. Right? It's going to have a constant speed, and so if there is a constant speed, this acceleration has a numerical value of 0. That means that this entire second half of the equation, I can actually just cancel it out, and so I'm left with this displacement being equal to the velocity multiplied by the total time, right? That change in time. But here's the issue. Look at this triangle here. We're actually only looking for the x component of this value. Okay, the x component of this value, and so this velocity here that I've written here as initial velocity is actually this 2.2 meters per second, which is the resultant. Okay, it's the resultant. It's the combination of both the x and y components. But here, I'm actually looking specifically for the x component. And so I'm going to have to use either the sine or cosine function, I haven't thought about it yet, and this 21-degree angle. So the question is, I'm looking for horizontal displacement, right? Horizontal displacement. Here's my angle. Should I use sine or cosine of 21 degrees? Right? So again, looking for the x component. That's going to be adjacent over hypotenuse. So that's going to be cosine. And so because I'm looking specifically for the x component here, I'm going to take this velocity, okay, it's going to be that total velocity, that resultant velocity, and I am also going to take the cosine of the angle, then multiply by the change in time. Now, you guys know how multiplication works, so I put the cosine in between the initial velocity and delta time. You could put it at the end, doesn't matter, because multiplication happens at the same time. This is just kind of how I was going to school, so this is how I'm going to represent it. So we are being asked to solve for horizontal displacement. We have an equation that will actually solve for horizontal displacement, so let's go ahead and plug everything in. Cosine, what's that, 21 degrees, and then multiplying by 0. What was it? 1/6. Is that right, or is that backwards? Yeah, 1/6. All right. Weird situation. My calculator just cleared my results, so you'll have to let me plug this in again. Sorry. Okay. Come on, calculator. I'm on TV right now. Don't mess me up. 21 degrees, and then I'm going to multiply by 0.16. Okay, sorry about that. So the question has given me two significant figures everywhere, and so naturally I'm going to report my answer with two significant figures. And now that my calculator is still actually showing the results, I can tell you that I'm going to report, let's see, I should do that to 0.33. 0.33. And you can see that these two values, obviously these three values are multiplying together, but seconds is going to cancel, and that's going to leave meters as my unit there. So my horizontal displacement is going to be 0.33 meters. Okay, that's only part of our question. We need how high does the flea jump as well. Okay, now here's the trick. We're going to be using part of the definition. So we have this flea made a jump, and it initially goes at this angle, but we know that projectiles travel in this parabolic shape. Okay, this parabolic shape, it's a parabola, and we're being asked about this middle point here, this middle point, the highest point, right? How high does the flea jump? We're not interested in where the flea started. We're not interested in where the flea landed, because we kind of already did that, right? How far did flea leap? Now we're trying to find out what is this delta y max. Okay, that's the question. Now, you guys know that once this projectile has been launched, and we're assuming that air resistance is negligible here, and we know in real life that air resistance is not negligible, but for right now, that's kind of the game we're playing. We don't have to pay attention to air resistance. With that, we know that this highest point is delta y, right? Because this is a y direction. This delta y max is going to be at a point of time that is 1/2 the total time. Okay, so and this is going to be a definition that you're going to use a lot. So I'll write it down here. Maximum height is reached in a time interval of delta t, right? Trust me, that's a t. Divided by 2, half of it, right? Half of the time. Okay, half of the time. So now that we know that, we're going to be using, again, this is a displacement. Okay, this is a displacement. And so we're going to use a kinematic equation. We're going to go for the total y displacement because that's actually going to be 0, right? Because the flea jumps up and it comes back down. Well, in terms of the y component, there's no overall displacement, right? It's in the same y location. But we're not looking for this kind of more regular, traditional kinematic equation. We're looking at something that has a time interval of 1/2 our time interval. So we're looking at delta y max, and again, we're going to be using the kinematic equation that looks like this, right? Because it has the values that we need. However, just like in the first part of this equation, we had to take into consideration some extra functionality here. We're going to be doing that same thing down here, because in the first half we were considering just the x component. Now we're going to be considering just the y component. So again, here is the angle. The y component is opposite over hypotenuse, right? Opposite over hypotenuse. And so that's going to be sine. So I'm going to have to take into consideration the sine of that. Again, I'm going to plop that right in there. And so I'll really be using an equation that looks like y max is equal to, okay, that initial velocity, okay, that the question gave me, times the sine of that angle. And again, I'm not going to use delta t. I'm looking for y max, and that maximum height is going to be found at a time of half delta t. So what I'm going to do here is I'm actually going to use not delta t, but half of delta t. Half of delta t. Plus 1/2 acceleration. And again, I'm not going to use my normal delta t squared. I'm going to be using this delta t divided by 2 squared. Because again, we're going for y max, and y max occurs at half time. But it's still squared, so I got to make sure I keep that along. Now, this it's going to be pretty darn annoying to plug into your calculator. It was for me. But we already have the equation set up in a way that we can plug stuff right into the calculator in this form, and it'll give us a nice answer. Okay, so let's actually plug this in here. Okay, so delta y max is equal to, okay, my initial velocity, 2.2 meters per second. Okay, I'm going to be using the sine of, what's my angle? 21 degrees. And what I'm actually using for my time is delta t over 2. So from the question, my time is 0.16. Okay, so my time is going to be 0.16 seconds divided by 2. And then, what else I got? Okay, plus 1/2. What is acceleration? Well, hopefully you guys know by now that when we're talking about the y component, acceleration, okay, and the y component is going to be essentially the force of gravity, but because gravity pulls things down, and again, according to our coordinate system that we've already defined here, that needs to be a negative sign, right, to show that it's going down. So that means that the acceleration is negative 9.81 meters per second squared. Right, so I'm actually going to plug in that. And then, again, my time value is actually going to be delta t divided by 2. So my delta t is still 0.6 seconds. Divide that by 2. But I got to remember that it's squared. And now we're ready to bust this out. So if I try to make this a little bit simpler on myself, you know what? I'm just going to trust that you guys can bust that down. If you were going to be doing this on a test and you wanted to make sure you're not biting off more than you can chew, I would kind of suggest you do your calculator work in smaller bits. And if I have, you know, done this correctly, which I'm pretty sure I have, this part of the equation ends up being 6.03 times 10 to the negative second meters. And this one over here ends up being, does that negative sign, a negative 3.1 times 10 to the negative second meters. And so it's actually going to be easier to kind of break those into a smaller piece, because there's always this chance of something funky happening with your calculator, right? That plus sign, that negative sign, right? Students still trip up over adding a negative number. But when we actually add this up, right, we end up with 3.2 times 10 to the negative second meters. Okay. So again, this middle part right here is something that I like to do, like when I'm actually working these problems, because I have a chance to kind of see if the individual parts make sense, and I get to see this kind of middle step to see if the middle step makes sense, and then I can compare that to my final answer. Some students ask me, should I represent this with a times 10 to the negative second meters, or should I turn this into centimeters? Because then I can represent it as 3.2 centimeters. I would say whatever the units the question gives you is what you should use, unless the question specifically asks for a unit to be used. And now in this question, there is no specific unit requested. So I do not care what unit you use in your answer. Now again, if I, like on your test, if I asked for a specific unit, like if I ask you to report your answer in centimeters, then you need to report your answer in centimeters, or you haven't done something that I've asked you to, and you therefore will not get full credit. But in this situation, I don't care, as long as the answer makes sense. What I'd suggest for you, if I don't ask for something specific, I suggest you simply stick with the units that the question uses.